Didn't see big problem in the homework assignments and quizzes. There's some minor issues. I will give you guys some feedback on that really quick. So first, the full scale output of the DAC. Is it VREF? No. Is it the resolution or the smallest change in voltage times 2 to the nth power? Is this the VREF, the full scale output of the DAC? Is it VREF as a reference voltage? Is it VREF? No, if you look at the notes, it's not VREF. So is it the resolution, which is the smallest change in the circuit, times 2 to the nth power? Yeah, it's going to be n minus 1. So what's going to happen is the full scale range of the output voltage of the DAC is 2 to the n minus 1's power over 2 to the nth times VREF. V full scale. Or it's VREF over 2 to the nth times 2 to the n minus 1's power. Okay, so what is this one? That's a resolution, right? Okay, here's the resolution. It's not 2 to the nth power, it's the 2 to the n minus 1th power. Okay, that's the first thing found in the minor issues in one of your homework assignments. And another one is DNL and NLs. That specific problem. So there's an easier way to do that actually. I would recommend you guys use the spreadsheet. In the calculator, if you are doing this in the exam, you don't have a spreadsheet to work with. So it's going to be, it just manually calculated, right? If you know the equation here, I just manually put the numbers in the different rows or columns. So these two columns are given, I believe, right? And then for DNL, the first one is just 0 because 0, the ideal one is 0, you are getting 0, so there's no error. Okay, so for both DNL and NLs, they are both 0. So for the second one, for DNL, how do we calculate DNL for the first one? Or for, if we add another column here, so this is 0, right? And this is 1. So it could be DNL or NL 0, DNL or NL 1, right? And 2 until 7. So DNL 0 is 0, DNL 1 is. So for DNL, we're comparing the actual step, the step size, to 1 LSB, which is the ideal step. Okay. So what's the step size for the how to find the step size in both actual and ideal? What's the way to calculate the step size? The current one minus the last one, right? That's the step size. So for 1, okay, you use 0.625 minus 0. See what I put here is B3 minus B2. That's a step size. And compared to the ideal step size, which is 0.625, which is a constant. It's not being changed over the time. And divided by 0.625. So we're getting how many LSBs is in there, okay? Because if you drag it at the bottom right corner, and it's gonna increase these two numbers automatically. So it's going to change B3 to B4 and change B2 to B3. That's what I did. So if you find out, select the next one, you can see it becomes B4 minus B3 instead of B2, B3 minus B2, right? So you just need to do the first one and just drag it to calculate all the rest for you. Make sense? Okay. For INL, we're not comparing the step size. However, we're comparing the height. So the current value. So just look at the height. So this is the absolute height over there, and this is a ideal one. So you're comparing the actual one with the ideal one, and the equation becomes B3 minus C3 and divided by 0.1 LSB, the voltage level at 1 LSB. So it's going to divide it by 0.625. Okay, so if you compare these two for the absolute height, these values in the table are actually absolute heights. So you can just directly use it. So the left one minus the right one, okay? Same for the second row here, and same here. So if you select it, you can find out this one, this cell is calculated by B4 minus C4 and divided by 1 LSB. And then just drag it, gets you all the INLs. So why I'm introducing a spreadsheet over here for you guys? What do you think? Because that's probably one of the tools you want to use in real life, in the real world applications. If you've got an ADC design and or DAC, right, and you simulate it, you find out all the values, you can actually measure it in your IDE, like LT-Spice or Cadence, whatever. You measure all the points, or you can probably just output all the values from the tool, and then import it to Excel sheet or Python or MATLAB, whatever, and you should be able to know how to calculate DNL and INLs. If you have a like 10-bit or 12-bit ADC, you definitely don't want to just handwrite on the paper and comparing, right? Must be some programming tools. That's why everyone has to take engineering 104 at the very beginning of the freshman year, because it's just being used all the places. Either MATLAB or Python, just so useful. Okay. Any questions on this? That clear? Okay. So if you are not using spreadsheets because you know how they are calculated, are you still able to just write them down on the paper in the exam and do the calculations? I know it's boring, but just be patient. Calculate all the numbers by hand. Should be doable. And I can upload this spreadsheet to the website as a link, so you can download it. Let me see anything else. Oh, for the labs. It's frozen for some reason. If you look at the simulation I got here, it's the background is white. Okay, so the reason I want you guys to use white is because in the future, if you have to use simulation in your homework assignments, that you have to print them out on the paper, so it's better to use the white color instead of black. It's going to be a big chunk of ink. It's not environmental friendly. And how to change the background color. So I'm recording, so you guys will find out later. Okay. So go to control panel, and I believe it's waveforms, and then color scheme. You can see there's the option regarding background. Okay, so for a white color, should you use 255 for all of them or 0 for all of them? 255 is white, right? It's the brightest. So 0 is just a 0, just no pixel, no values. Okay, so if you have all zeros, it's black. It's RGB combination to make all the colors. So you want to use 255. And also for the traces, if you look at mine, the traces are a little bit thicker than yours, so it's easier, it's more visible. And also you see the frame is also a little bit thicker, including the font, the numbers and the units. It's just slightly bigger than yours. I think it looks better than the smaller ones and thinner ones. It's just more visible and more professional as a presentation, how to present it. So how to change all these things? I think for axis, you can change it to black, which is all zeros. That's what I have over here. Instead of having a gray or light, dark, let's just use black for the frame. So I have to do axis. That's going to change the frame to black, just black lines. And grid, I don't know if I have grid or not. So I do have grid. So the grid is not, seems like the gray color, not too dark, which is not that important. You don't have to change all the traces color, just use the default values. And for the numbers and letters, the font size, you can change it over here. And the color of the letters, see, I don't think I changed anything there. Maybe use a bold font, okay? Just a little bit to make it more visible and looks prettier, okay? And for in the future, for electric VLSI schematic design, the drawing and the layouts, it's required for you guys to show the error-free message. If you don't show it, I'm going to take points off. So I didn't do that for the first one since I didn't tell you, okay? But now, from now on in the future, you have to show 0 errors, 0 warnings in order to get the full credit. That makes sense? So I have to show that message window and also the simulation result as well, like this, okay? And also the connections in between, for example, the ADC and DACs. So these are fine, okay? Just not straight lines. But if your connections are just everywhere, looks unnecessarily messy. It looks like you can just spend another 30 seconds to make it looks better, but just didn't do that. I'm gonna also take some points off from that. Right. You have any questions regarding the labs? It's been straightforward, right? Because the instructions are relatively clear. Okay. I think that's all the things I found from your assignments. If you don't have more questions, I'm going to move forward. Okay. C5 technology, 500 nanometer, and it's using a lambda rule, which is the smallest size of the feature in the circuit is 300 nanometer, which is 1 lambda. Okay, even though the C5 stands for a 500 nanometer technology, however, we never use 500 nanometer in the circuit, and we don't use 300 nanometer as the length of the transistor in the circuit as well. So what we do is we use 2 lambda as the smallest either length or width. For the CMOS transistors. So 2 lambda equals what? 600 nanometers, right? It's not 500 nanometers. Even though the C5 technology can make the smallest feature or transistor in 500 nanometers, they claim that, right? They might be able to make that happen as well, but the yield will be low. So there will be more mistakes if they do fabricate transistors in that dimension. So to be safe, we use the lambda rule. So one lambda is 300 nanometers, and we usually use multiples of lambdas in the circuit in our layout. And the minimum we are going to use is 2 lambda, which is 600 nanometers. It's slightly bigger than 500 nanometers just to be safe. Just make sure they can fabricate it without making any mistakes. Does that make sense? So you guys are using, I think for the preferences, when you set up electric VLSI, you put lambda as 300 nanometers in the setting. I don't know if you still remember that. And when you resize your transistors, we never use 1 lambda. We never use 1. So if you look at for example, you got a transistor here in electric VLSI, remember it only shows 1 or 2, or 2 or 3, or 10 or 20, right? It never shows the units. If it shows 1 versus 2, what does that mean? What's the size of the transistor? That's right. So it's going to be 300 nanometers versus 600 nanometers. That's the real size of it. Okay? And there's three layers of metals. That's the most important feature you need to know whenever you hear new technology. You want to know how many metal layers they have. So for C5, they have 3. For different technologies, they may have like 5 or 6, which is being written in the NDA. I couldn't disclose it. But for the ones we are going to use, we are using for the senior sum, is or the tape out project, it's more than 3. So it's, 3 is a really one of the oldest technologies, and I think the first version of the 6502 WDC's microcontroller from Mr. Bill Munch, I think that one was 2 metal layers, and they can use just 2 metal layers to lay out the CPU chip, microcontroller, that can control a LED or a 7-segment display, which is amazing. So why that matters? So what if you're only on 1 metal layer? What's going to happen? Cross it, right? It's going to short the circuit. So that's why our PCB, the ones we have been making, fabricating, or sending out for manufacturing, is 2 metal layers, 1 top, 1 bottom. So you can see the red and blue color in Eagle PCB, just 2 metal layers. But it can make up to, I believe, like 60 plus something metal layers in the PCB. The cost will just be slightly higher, right? But we're not necessarily making 60 plus layers, but making like 4 layers of PCB is really common in industry. So 2 is just for hobbyists or beginners. We just make it cheap, like $5 for 5 pieces. Super easy. So you know that if you have more metal layers, you got more flexibility to route the metal traces. Okay, so C5. That's right. Yeah, you can put components really just next to each other and never worrying about routing the traces, because you can always go up and route traces on the top, right? So see, if you look at the like our PCB design for microcontrollers, we still put the components pretty apart from each other. So we sometimes still worry about the routing. But if you have like 4, 10 layers, you just put them next to each other. It's going to be fine. So all the vias and traces are running in the intermediate layers instead of on the top or bottom in the visible layers. So the computer's motherboard, if you open it up, or your smartphone's motherboard, the PCB, you can see the components are really close to each other. There are probably more than 10 layers in it. So C5 provides 3 metal layers. And this is a cross-sectional view of it. All right. The first layer is called Fox. This can be a little bit confusing. It's filled because it's not really flat. It's filled oxide layer. It's being used to reduce the crosstalk between transistors, which may cause lower threshold voltage. But if you look at different figures or different pictures online, they all look different. Even the one from the textbook, because it's not really flat. So that's why I was trying to find some real pictures of the transistor. Someone cut the cross section and look from the side, from the ICM, and it looks like this. So that's a real transistor. But maybe they fabricated different things on the top. But the bottom process should be the same. So if you zoom in, so this is the substrate. Okay, this is the substrate, the silicon substrate, and that's a gate. Okay, that's a diffusion, which is N plus or P plus. Right, and this is the via, has a metal via. It's made by tungsten. It's a metal material, and drills a hole to the top layer and routes the metal one. It's aluminum material, so metal one traces over here. And the Fox, which is filled oxide, is this one. Did you see the little very thin layer here? It's very dim, but can you see it? Okay, so it's not really flat. So when you fabricate a transistor on the substrate, it opens up the field. So the filled oxide opens up the Fox layer and expose the substrate, and then dope N plus onto the substrate or into the substrate. And also they dope a polysilicon layer as a gate on the top. So the way to fabricate it, I can give you some examples for lithography, so you get some concept regarding how to fabricate different layers. It's called bottom-up fabrication process. So start from the bottom. Ian did some lithography with the microfluidic chips. So the way to do that is have a wafer here at the very beginning. So how do you fabricate different layers on the top with different materials, for example? Okay, so the first example I'm going to show you is, okay, just a silicon wafer. We are not making a transistor. Just show you guys a very simple, it's called photolithography. That's a metal piece on the wafer. This is the final product. Okay. This is something I want to fabricate. How do we do it? You grab a wafer and place the little metal piece on the top by hand. This corner, the resolution of this corner, you should know, it's in the nanometer resolution. You know what I mean? So which means the corner here is in nanometer resolution. If I'm telling you to make a metal piece like this, it's not going to be like this. Okay, it's exactly the same height and same width, same length, and in the nanometer range of the variation. So first, you have to put a mask on. You need a material called a photoresist, which is the photosensitive material that in the gel form that I can pour on the wafer to protect it and then to manipulate the different layers. But now before we do that, so the process looks like this. So we gotta grab a wafer, right? So we know we need a metal layer on the top. So at the very beginning, we just spin, no, it's not spin coat, it's deposit. You can use CVD, it's chemical vapor deposition. So the way that works is you place a wafer in a vacuum, okay, and you make the metal material into chemical vapor form and deposit it on the wafer. Just place the wafer in the vacuum chamber and then it's not spray, but similar to spray, just emit or spray the chemical vapor of the metal particle into the chamber. It's going to deposit onto the top of the wafer. So the thickness of the metal layer is determined by the time you deposit the material and the concentration, I believe. So it's a controlled environment. So you can control the thickness of the metal layer, okay, depending on time and concentration and maybe other parameters. So you know that you can deposit the metal layer on the top, okay? So there will be a homogeneous metal layer on the top. And the second step, you place the wafer with a homogeneous metal layer on the top onto a spin coater to spin coat a chemical called photoresist. It's in the bottle. You can pour it on the wafer. And you spin coat it to make it a homogeneous layer as well. Okay. So how do you know the thickness of it? So what's gonna determine the thickness of that? Yeah, how fast and how long is not actually how long. It's just how fast. So how fast you spin it, and also the density of the photoresist. If you have a different material or from a different vendor, you may need a different speed. If it's thicker, then you probably need to spin it faster to make that same thickness of the photoresist. Okay, it's like honey. You pour on the top, spin coat it. Okay, and this material is being really strictly controlled to import it to be exported to China. And I think Japan or another country is making that. Only 2 or 3 countries are able to make that photoresist in order to make a 5 nanometer resolution on the chip. So there are just so many things are being controlled. You have to be able to get all the things as a collaborative effort from all the companies in the world in order to make it happen. Anyway, so this one is a photoresist. You pour on the top, spin coat it, you get a certain thickness of it, okay? And then you apply a mask. You can design a mask in AutoCAD, or there might be a different tool, EDA tool, that I can design a mask and place the mask on the top. So the mask has ink. Usually it's a chrome material, it's metal ink that can block UV light. But you can design the mask to have an opening so it's clear as a feature, it's clear channels or something, right? So it's clear. When you expose it to the UV, ultraviolet, the laser, and the ink is going to block the light, but it's going to reach the photoresist material from the opening here. Okay. So this part of the photoresist is photosensitive. So after it's being exposed to UV, it's getting cured. The texture just changes. And because the mask is not like honey you sprinkle on it. It's just a glass plate or a plastic film. So put it on the top of this thing, right? And then you expose it using UV, so you can remove it just by hand, for example. Okay. And next step, so this is UV exposure, mask, and UV exposure. And next step, you remove the mask, and which gives you a homogeneous metal layer on the wafer, and a heterogeneous layer of photoresist on the top, because this part is being cured. It's a different texture, but the rest are not. Okay, and then you immerse this thing in a chemical. The chemical is called developer. So developer is an organic solvent. It's gonna dissolve the other areas are not being exposed, were not exposed to the UV, but the cured ones are resistant to the developer, so they will stay. The next step, after being immersed in the developer, you're getting this. That's a homogeneous metal layer still, okay? I got a piece of metal, no, photoresist, cured photoresist on the top. So what's next? How to remove the metal? No, some sort of acid, right? So it can etch the metal. Because the photoresist is on the top, it's going to cover this area of the metal, so it's going to protect it. Okay, so what's going to happen is you are having this. After putting the acid and etch it, eventually you are having this. So this piece of metal is being protected by the cured photoresist. It's not being etched away. All right. So look at this. We're fairly close to the final result, right? This is what we want. Okay. And this is what we have now. What's the difference? You have a cured photoresist on the top, right? And then put in a chemical called stripper, which is designed to remove every organic or chemicals on the top, but not metal. So cured or not cured, doesn't matter. It's going to remove the cured photoresist on the top, and eventually just leave a piece of metal on the top, okay? So now I got the final product like that. So my question for you guys is, why we don't print it using a printer, but we use a photoresist instead of a printer? So if we got a, do you know why we don't use a printer? Or any kind of like 3D printer that can spray traces onto this guy. So we, for example, you know the ink from the printer can protect the metal. That's how they make the PCBs, basically. So in my senior sem, when I was an undergraduate, what I did was I bought the double layer metal plate, which is the PCB board originally. Doesn't have any circuits on it. It's just the copper plates on the two bottom and top. Okay, and then I designed the circuit, just draw it on the paper. Any of the paint tools in computer, just draw it, draw the circuits, and print it out using a plastic film, I think. It's glossy plastic film. So the ink is not getting to the paper, not being absorbed by the paper. It's a plastic film will keep the ink outside of it, right? And then I put the side, which has an ink on it of the plastic film, onto the copper plate, and then use iron on the top to heat it up to transfer that traces of ink onto the copper plate. And then I put the copper plate into a solution. I forgot I think it's Fe3Cl3 or something. So which will etch the copper away from the copper board, but the traces of the ink the ink traces will protect the copper underneath it. So eventually you got a copper. What's happening was you got so this is the PCB board, okay? And you have all the traces. For example, this is one of the traces. On the top, you got an ink trace on the top, just protecting that metal trace at the bottom. Okay, and then I just I think the ink was pretty easy to remove. I forgot how I remove it. Probably just by a wiper or something. I just removed the ink, so I got the traces on the board. That's how I made the PCB board. I believe they use a similar chemical and technology in GL3 PCB, GL2, I forgot the name, GCL PCB, right? GLC PCB. They'll use the similar technology. Okay, have to use the layer or a material on the top to protect the metal, and then etch it and then recover it. Okay, similar. So why we are not using ink for the chip design, like how we made PCBs? That's right. I think even for 1 mm resolution is pretty difficult for these printers. Yeah. So photolithography can give you nanometer resolution. I think for the photolithography tools we have or equipment we have in the lab, we can make down to 1 micron. But for the e-beam lithography of the SEM on the 3rd floor lab of Dr. Jessings, I can make probably down to 50 nanometer, a dot, I think. Different layers. Introduction to photolithography, so I don't know how they make different layers. And I want you guys take a look at the fox. So we got a concept of the fox over here in real world, okay? But when we draw it, it could be slightly different. You can see one of the cartoons I found online. That's how people draw it on paper usually. It looks different. So seems like this green layer should be the fox, but actually it's not. It's just a regular insulation layer. Okay, and the fox is being used as separators, maybe in between the transistors. This is the one transistor, drain source gate, and there's another transistor. So it's in the middle to reduce the crosstalk between these transistors, which may change the threshold of the transistors a little bit, but it just put something in the middle to minimize that. Okay, that's a field oxide. So the way they made it is at the very beginning, the field oxide, the fox here, it's just everywhere, just one homogeneous layer on the surface of the silicon substrate. Okay, and when you need to design or in your design file defines a transistor in this specific location, it opens up the fox layer. Remember how to open it up? How can I open up the layer on the wafer? Photolithography, yeah. So it might be very complicated process, but you can imagine how that works. So you at the very beginning there was a fox on the top, right? very similar to the one I just showed you, right? So at the very beginning, you can grow. Usually they use the word grow. A silicon dioxide on the top of the substrate. So for example, this is the Fox. What's the technology being used to grow some material on it? Remember? What's the name of the technology? No, to grow it. We're not etching it. Etching, you need lithography, right? But now we are growing. You have to deposit the layer first, and then expose, then photolithography. This is solid. It's not a liquid form. You cannot spin coat it. But you have to have the material first. That's how you make the material, right? How to make it happen. But now you have the material ready, and deposit on the top of the wafer. Yeah, I mentioned that really briefly just now. It's CVD. You should know this actually because this, I believe, have you ever in Dr. Jessen's 430 class? 430? You were?
Yeah, I thought we had like a gas into the oven,
mm-hmm.
like a heat chamber, and then there's oxygen still.
Oh, you
drive in the oxide.
On the wafer?
Mm-hmm.
Interesting. Okay. But I think there's another way to do that is chemical CVD, right? Did you do any? We don't have a CVD here, it's pretty expensive. Chemical vapor deposition. So how do you open it up? Etch it, right? Could be photolithography, could be something else. You just have to use a mask. Or there's another technology, I think, that it can etch oxide on the top. So in so for example, if you open up the Fox, open it up, right? And then you start put the gate and diffusion here to make a transistor. And there's another oxide layer in the middle, which is called GOX, gate oxide. So since we're here, I think it's better to just talk about the what are the layers in lec12 for this concept. So if you look at this, for example, now we open it up, and it's called active. So active layer opens up. This may answer a lot of questions in lec12. So this is called active layer. Opens up. I believe you grabbed the little nodes from lec12, right? Has a node in the middle, and then slashes or dots. Remember? Okay, and some you see the names, some like N, select, N active, or P select, or P. I think it's just use P act, not P active, just N act, P act, N select, P select. And you probably can notice that the N active is smaller than N select. So the inner one is N act, and this is N select. Is larger than N act. So N act opens up the Fox, so you can see it's aligned because exactly the same size. You have this layer and it's going to open up the Fox in the same dimension as your active layer. That's how they design it. Okay, so the active layer is going to open up the Fox, and the unselect layer defines the window here's a window, okay, that dopes N plus into the wafer. So my question is, why your N select is larger than N active? Why N select? So the way that works is you open up the Fox. Okay, so I have an opening here and expose a P substrate that I can dope the diffusion or the N plus material into it. And now when you dope it, the window you are going to use is going to be unselect instead of unact. So you want the unselect to be slightly bigger than unact as a window that you drop all the N plus material into it. So you can imagine there will be some N plus will drop onto the Fox, right? Because it's bigger than the opening. Why we wanted that to happen? To reduce misalignment. You got an opening and you think I just use the same size of the opening to drop my N plus material, I'm going to drop a perfect N plus, which is just right at the boundary here, into the opening. It's impossible. Imagine this is in nanometer level, there will be a lot of misalignment. So what's going to happen is just make a window to be bigger, even though you are dropping some N plus material to the Fox, since you are not using the Fox for anything, which is fine. All right, but I can make sure that all these areas starting from here are getting the diffusion material or the N plus material into it. Does that make sense? Okay. There might be a question in the homework assignment, why N select is bigger than N act? You know how to answer that, right? So when you draw your layers of transistors, just use the Fox like this in the middle of the transistors. If you don't have a transistor, being fabricated on the wafer, so the way you draw the layers is going to be this. So that's the bottom from bottom up. That's a p-type, p-stop. The first layer will be Fox, and the second layer is silicon dioxide or insulation. It's silicon dioxide, and so you can run gates. You can make gates in here. It's a polysilicon material, or as a gate. And then one layer up, it's an insulation as well. But inside the insulation layer, you can have metal 1. And one more, metal 2. So all these metal layers are in the insulation layer, so you are isolating them from the other metal layers, so they're not going to short it. And one layer up, that's metal 3. Do you have metal 4? No, C5 only has 3 metal layers, remember? And the way you connect the signals to the circuit or output signals from the chip to the outside world is to have an opening on the metal 3 layer, because this is the only layer you can reach. There's no way that you can have a metal 2 layer and you drill a hole here and have an opening, bound a wire to it. No, that's not possible. So when you do that is there's another layer on the top, it's called That's the name of it. It's a passivation layer. I may spell this wrong, but the passivation layer will open up the insulation on the top and leave an opening on the top. In electron VLSI, you can select that layer to open up the window on the metal strip. And then you can bond a wire to a metal plate on the chip, and then you have a pins connected to the metal plate in the package. So you can plug in this one into a breadboard. Make sense? If you need a signal from the transistor from the gate, you need a via to metal tray, and then open up the gate or open the transistor's channel to run current in the channel. Make sense? I'll keep talking about the CFAP layers next Monday. Okay. And homework 3 is due next Friday, so you'll have the time to work on it after the Monday lecture. You'll be ready to do that after that. Okay.